to share the screen? Actually, I do not know. I'm trying in my pad, but I am not seeing any options for that.
I'm now allowed to share the screen. 1 second.
Yeah, please. Then please go ahead. Thanks.
There you go.
All right. Looks good.
Yeah, 1 second.
Mm-hmm.
You can see the pointer?
Yes. That's perfect. Perfect. Slides are moving nice. I think all right. Yeah.
One last thing. Just, you can see this.
Yeah, I can see the pointer as a picture. Everything I can see.
1 second. Now you can see this movie.
Yes, I can see the movie also. Yes, it is working. Great. Perfect. Maybe we can wait for a few minutes.
Yes,
people
sir.
will join slowly. You will see.
No problem. I just put, I go on mute.
Yes. Okay, so hello everyone, good afternoon. Welcome to our weekly seminar series. First, I invite Dr. Vaibhav Pant to introduce the speaker and then requesting him to deliver the seminar. Vaibhav, go ahead.
Yeah, thank you very. Good afternoon, everyone, to this weekly seminar series. And today we are happy to have Dr. Sharavan Hanasoge with us. He is Associate Professor at the Tata Institute of Fundamental Research.
Okay, so hello everyone, good afternoon.
And
welcome to our weekly seminar series. First, I invite Dr. Vaibhav Pant.
There is some echo.
Okay,
or
I'm not sure
something.
what is happening here. Yeah, okay. Dr. Shravan is recently award in 2021 by Indian Institute of Astrophysics for his work on deciphering the internal structure of sun, star, and the Earth. So today he will talk about seismology and physics of sun and stars. So Shravan, please go ahead.
Thanks very much for the opportunity to give this seminar, and thank you for inviting me. So let me begin right away. So this work that I'm going to be presenting is actually a summary of many topics that our group pursues at TIFR, and so in collaboration with a number of students and postdocs and other faculty members abroad. So they're very involved in these efforts. Okay, so let me begin with the sun, and then I'll proceed to stars. So a lot of this talk is primarily on seismology. That's the dominant fraction of the work that we do is in various topics of seismology. So here is a nice video that many of you may have seen or not. If not, it's quite a fantastic video. This is a continuum image of the sun taken by the helioseismic and magnetic imager. It's on board SDO, which is the Solar Dynamics Observatory. And what you can see here is basically the photosphere of the sun and the formation of magnetic fields. And so you see these dark structures on your right, and then there's a little bit of this dark stuff that's forming on the left. And these are basically sunspots, or active regions, as we call them. And it's very interesting because the ones that you saw first seem to have basically disappeared, and the ones that seem to have come after have gained significant prominence, and they're alive for much longer, as you can see, and much bigger as well. So this video is sort of central to all of the complex physics that drives the outer parts of the sun that, in which we're very interested. One is the formation of magnetic fields, such as these. These are very strong concentrated magnetic fields. Where are they generated? How are they generated? And so on. So that's a central topic, in fact, of modern, and it's always been a central topic of solar physics. And so it's connected to various aspects, such as convection in the outer envelope of the sun, rotation, differential rotation. The sun has rotation that changes as a function of radius and latitude, meridional circulation, which is the motion of fluid from the equator to the poles. So there's all of these complex fluid, magnetofluid interactions that are happening. And this video encapsulates the outcome, in some sense, of all of this very complex physics. And so with seismology, we attempt to unravel all of the different aspects that we think give rise to this type of behavior. So let me continue. Yeah, so this is an image of rotation, or inferred rotation. So solar differential rotation is perhaps one of the most important inferences that we've obtained using helioseismology. And what it tells us is, maybe let me just briefly describe how it's obtained first. So modes, which are oscillations, global mode oscillations of the sun, are typically expressed in spherical harmonics, for instance, and the different modes are sensitive to different parts of the sun. So sometimes modes are sensitive to deeper layers and shallow, and then others are shallow layers. Some are sensitive to higher latitudes, others to lower latitudes, and so on. So by combining these modes in different ways, they provide a way with which to image different parts of the sun. So this particular picture that you see here is an inference of differential rotation, which is to say that this is the rotation rate plotted as a function of radius and latitude. I mean, both of these, of course, are radii, but this is increasing latitude. And this has been obtained using helioseismology. So waves that are propagating in the direction of rotation are sped up, and waves that are propagating the opposite to the direction of rotation are slowed down. So by using that breaking of symmetry, you can estimate the flow speed underneath. And by combining different modes, as I said earlier, you can see modes that are closer to the higher latitudes are affected in different ways than modes at the equator, and similarly as a function of radius as well. So this is one of the most important and robust inferences of helioseismology. It's withstood the test of time, and it tells us something very remarkable and unexpected. The thing it tells us is that the equator rotates much faster than the poles. No, not much faster, sorry, faster than the poles is what I should say. So this color shows rotation rate in nanohertz, and it's 453 nanohertz at the surface of the equator, and we don't really know what helioseismology can't really give us estimates closer to the pole, very close to the pole, but it's about 380 or maybe even 300 nanohertz. It's as dark as this color bar goes. So we don't know what this region is, but it's certainly as a very clear trend that the rotation rate is decreasing as you go to high latitudes. And why this is set up, how it's set up, and so on is is one of the most important questions in solar physics, and a very important question in astrophysics as well, because we know now from the seismology of distant stars that they display this type of differential rotation as well. So many solar-like stars show solar-like differential rotation, which is to say a fast rotating equator and a slow rotating pole. And yeah, so there must be there's presumably some robust connection between convection and other phenomena that are resulting in this type of rotation behavior. And we don't know what that is, but we know it's very crucial because it also has to do with how magnetic fields are generated. So understanding differential rotation is critical to many of the most fundamental questions in stellar physics. Now, the other thing that I spoke about was meridional circulation. So we know that from the equator to the pole, we can directly observe using Doppler and a variety of other ways, seismology and so on, that the flow there's a mean axisymmetric flow that's going from the equator to the pole. Now, what's not so clear is where that flow is for mass balance. It has to go back into the interior, and then the flow has to close. It has to be a loop of sorts. But we don't know what's going on here deep inside. This is one picture by these guys, Zhao et al. And Rajguru and Antia, for instance, have a different picture, which is the flow just goes up, and then there's only one cell and it comes back down. There's no question of these two cells. Here there's two cells. There's a cell that does this. There's another cell that's in the opposite direction doing this. And so this is a major unsolved question, and it's very important because, again, it's a type of conveyor belt for the transport of magnetic fields in the sun. And understanding meridional circulation and constraining it properly in the deeper layers of the sun is very crucial towards making progress towards our challenges in solar physics. Okay, so those are two large-scale axisymmetric circulations. Now there's lots of non-axisymmetric stuff as well, such as convection. What you're seeing is a numerical simulation of three-dimensional global convection in the sun. These images are products of millions of core hours of computation, and so very expensive to compute. So this is a model, solar-like model of convection. I believe it goes all the way down to the base of the convection zone and comes up very close to the surface. And this is at the deep layer, this is at the surface layer, and this is vertical velocity. So this is radial velocity rather. So this yellow stuff is fluid that's coming towards the viewer, and the dark stuff is fluid that's falling in. And you see these very neat cellular type flows. And these are the scales for these two flows. But we don't think that this is what's happening. This may not be happening in the sun. And the convection is very crucial towards maintaining these large-scale axisymmetric circulations that I was telling you about. But we don't understand convection. It's one of the least understood aspects, in fact, in stellar physics. And there's no a priori way of understanding it because the parameters that govern solar convection and stellar convection are just simply beyond computing capability, to contemporary computing capability. So we have to use helioseismology to try to cast light on these, on how convective cells are shaped and how they behave inside the sun. But this continues to be a major unsolved problem. Now there's a more recent problem, which is also quite a fascinating one. And these are that of Rosby waves. So these were observed a few years ago by the German group, and several others have replicated it, including our group. And the thing is, all spherical bodies of fluids, if you will, display Rosby waves. So the Earth has Rosby waves as well. They're basically what we call jet streams, and they create a cause of various weather events and so on. And so they also do that in the sun. But they're very remarkable in the sense that all the Rosby waves in the sun are very close to the equator. They're equatorially dominated. They don't seem to exceed 30 degrees above the equator. And they're all symmetric. They're symmetric about the equator. So if you look at this, they preserve a certain symmetry about the equator. So we don't understand in terms of radial vorticity. So if you put your finger out, I'm sorry, this finger is pointing inwards for this one. But if you plotted radial vorticity, then you'll see that basically it's symmetric about the equator, and we don't know why they're only symmetric. The other remarkable thing is that these Rosby waves are not really easily observed in numerical simulations. They predict different types of behavior, in fact. And so there's something very different between what's happening in the sun and what's happening in numerical simulations. Some fundamental ingredients that are missing. I don't know what those ingredients are, but clearly it's something important, because what we observe in the sun is very different from what's happening in numerical simulations. So there's some important physics there. And so the question of this dissipation and excitation mechanisms for Rosby waves is an outstanding and important problem. Okay, so what we try to do in our group is to push the frontier of precision stellar physics. And so with data, with sophisticated data, long-term data, in fact, of the sun as well. Now we have 3 decades almost of data of the sun. Not quite, but getting there. We've now precision, the ability to be precise, has greatly increased. And so, what's changed in time is that we can now make very minute inferences of what's happening inside because of the precision of the data. And so theories and techniques have to develop as well in order to achieve that type of precision. What was considered precise 25 years ago theoretically has of course changed now. And so we have to be at the forefront of this type of physics. You have to develop theory and techniques as well, and sort of catch up with the data, if you will. And so, as I said before, we have very long time series and very high quality time series of these objects of the sun and stars. And these are oscillations, for instance, of the sun and stars. So with these data come, computational expense. They're not easy to necessarily do the analysis. And so you need to use cutting edge techniques in computing, and understand what the physics questions are and deploy the computing appropriately and so on. And so the goal of our group over the past few years has been, can we understand the sun and stars better if we develop these theoretical and computational models to attack these data? Okay, so one branch, as I said, of the work, basically focuses on the sun. So I'll describe this technique called normal mode couplings. Very beautiful technique. It was developed by other people in helioseismology, but we've really, but it's in a fairly nascent stage. It actually has not been, it's not mature in some sense. So we've taken this method and sort of run with it. And I'll describe many results and many exciting future projects that are to come. So let me just briefly describe what helioseismology is all about. So here is a movie taken by the Michelson Doppler imager. It's a space-based instrument. And you see this static stuff near the equator. These are the acoustic waves, 5-minute oscillations, if you will, of the sun. And these are basically known as 5-minute oscillations because their periods are on the order of about 5 minutes. And we observe very long spatio-temporal series of these. And so on this disk, we have a decade, 2 decades, 3 decades long worth of high-quality oscillation data. And so the basic idea, now we understand this now, is that these waves are set up at the surface by turbulent convection. They propagate inside the interior and they're deflected away from the core. because of the increasing sound speed. And they come back up to the surface, they reflect, they bounce back, and so on. And so depending on the structure of this, on the distribution of sound speed and other properties of the interior, there are certain resonances that can be set up. And so, for instance, you see the blue line, that's a specific resonance. And this is the acoustic cavity. The blue line is, as you can see, the same radius. It's a cavity that traps this mode. And the red line, as you can see here, is a different mode that goes much deeper, and it's trapped in a different cavity. So you have all of these resonant oscillations of these modes, each sort of plumbing into different depths of the sun and sampling different layers. And these waves, basically, they show up at the surface after going into the interior and rising back up to the surface, and then they perturb it. And so you see oscillations. Basically, that's what you see in the video above. And these are waves that are hitting the surface and perturbing it. And so we measure long time series on this disk of these perturbations, velocities, if you will, of the surface. And so by performing a spherical harmonic transform, because the sun, as you know, is a sphere, so you transform theta and phi, latitude and longitude, into Lm. So this phi here represents velocity, which we measure, represents spherical harmonic degree, and is azimuthal order. And so this is just a standard spherical harmonic transform. Note that we can't see the far side of the sun. So the far side is just replaced with zeros. So we only see the near side. And so we take the near side data and we replace the far side with 0, and then we perform a spherical harmonic transform. And this is temporal frequency omega, because we transform even the time series into frequency domain. Okay. And so what is seismology ultimately, right? So basically the idea is you have a wave operator. So you have a wave equation, if you will, of the sun or of any object, for that matter, that describes the propagation of waves inside that medium. And there are coefficients to this wave equation. So for the simple case of acoustic waves propagating in air, you have the sound speed of the air. But you can have more complicated things. For instance, in the sun, you have the acoustic speed as a function of depth. You have pressure. You have an adiabatic index, which is a type of equation state parameter. All of those actually do affect the acoustic waves. So you have a number of parameters that are sitting in the acoustic wave equation that describe the propagation of waves. And the goal of seismology is to find the best fit for all.
A question.
Yeah, please.
These waves, are they purely acoustic waves, something like we find in Earth, or these are magnetoacoustic waves?
So just to say, one second. Sorry, who is it? 1 second.
Indranil here.
Sorry, who is it?
Indranil.
Right. Yeah. So in the Earth, actually, you have elastic waves. So you have acoustic waves only in what is known as the outer core of the Earth, where there's a liquid layer. But for the most part, you have elastic waves in the Earth. So in fact, we don't observe elastic waves because the medium of the sun is a fluid. So stress has to be isotropically distributed. So pressure is the restoring force for acoustic waves primarily. And so that's an isotropic thing. Whereas elastic media, you can have anisotropic stress distributions. So we observe acoustic waves only primarily. But you're right, you can have magnetohydrodynamic waves in regions where the magnetic field can be, are significant. So for instance, if you look at wave propagation in sunspots or in other regions where the magnetic field is strong, then they become magnetohydrodynamic. I mean, ultimately, of course, the sun is a weakly magnetized medium. So you could say that they're all magnetohydrodynamic. But for all practical purposes, because the effect of magnetism is so weak, you can ignore the magnetism of the weakly magnetized medium at any rate. So the plasma beta is extremely large. I mean, so that's acoustic pressure divided by magnetic pressure becomes very, very large. So in some limit, you can just throw out the magnetic terms and you can keep them to be acoustic. Does that answer the question?
Yeah, it's fine.
Yeah. Okay, so so here is so the idea is to find the best fit coefficients for this wave equation, and so there are different ways to do it. The ultimate idea is to look at the spectrum. The spectrum of an operator is basically the set of eigenfunctions and eigenfrequencies. And through these quantities, you can find, by analyzing these quantities with these measurements of eigenfunctions and eigenfrequencies, you can find the best fit parameters for sound speed, for equation of state, and all these other terms. And so that's ultimately the goal. Now, there are different ways to achieve this. And I will talk specifically about mode coupling, which is, as I said, has been around for nearly 3 decades. So Woodard, 1989, is the first instance of its appearance in solar physics or helioseismology, but really there's not been that much work on the method and what it can do and so on until recently. And we're sort of spearheading this work. So the idea is that you have the reference model, which is a simple reference model of the sun. So for those of you who know solar physics, there's a model S, which gives you the properties of density, sound speed, gamma 1, which is the adiabatic index, and so on as a function of radius. Simple 1D model. It doesn't have rotation, doesn't have convection, it's axisymmetric, and it's non-magnetic. We know the sun is exactly the opposite of all of these and has all of these complications. And so the question is, how do we move this reference model? What additions to this reference model do we need to make so that it looks more like the sun? And you know, the hope is always that we're in the limit of perturbation theory, simple perturbation theory. So if basically the hope is that these are small deviations from here to here. And it turns out that, astonishingly, that is actually the case for the most part, with the exception of sunspots. Even though you would think that the reference model is actually very different from the sun, it's really not, in the sense of at least these quantities like eigenfunctions and eigenfrequencies, not so crazy. We're not so terribly off. And the idea of a mode coupling is that this reference model has a complete and orthonormal set of eigenfunctions. You can demonstrate this for the wave operator for the sun. It's a linear wave operator, and so these are very, very well behaved and very nice properties. So the sun has a different set of eigenfunctions, and so you have zeitcase sun, which is each eigenfunction of the sun. It's a combination, linear combination of the eigenfunctions of the reference model, and that comes from this completeness property. So every eigenfunction of the sun can be expressed as a linear combination of the reference model eigenfunctions. And there's a weight term here. This weight is known as the coupling coefficient. And so you have sum over k prime. It's okay, I don't need to really get into the mathematical details, but we can measure these coupling coefficients. By measuring these coupling coefficients, we can figure out what we need to do to the reference model to get it closer to the sun. And so this is the broad principle on which the type of seismology that I'm talking about rests. So this method is very powerful, and this has just not been understood as well as it should be, and it's only very recently that we've started to appreciate it. And it's not well adopted still, which is a little surprising, but not all that surprising, because there's a general inertia, of course, because people have their own methods that they like, and they're reluctant to change over. But okay, so the most remarkable thing about this is this is not in the right order. This is it. This is this superior signal to noise. So in some cases, we can see orders in magnitude improvement in signal to noise, which is just remarkable, because I don't think people expected anywhere close to the type of improvement in signal to noise. And ultimately, that's because the measurements that we make in mode coupling take into account the entirety of the mode. We do it all in spectral space. And so we use the entire modal information, the entire modal content, all seismic information is basically accounted for in this analysis. And so there is simply just no more information. And so we've sort of maximally and optimally using the signal present in the data. And so in many cases, of course, other methods are doing okay, they're not doing terribly, but in some cases, this is just remarkably superior. So that's one thing. And this other thing, which is a technical aspect, has to do with the fact that because we don't observe the far side of the sun, there is spatial leakage. So if you think about Heisenberg's principle, if you window a function in space, for instance, then you lead to a broadening in spectral domain. So in other words, if you lose information in one, if you try to isolate something in one, it expands in another. And so basically, because we don't have information on the far side of the sun, that basically means we're shrinking the window in space. That leads to a broadening in spectral domain. And that leads to various other systematics that I won't really describe. But it turns out remarkably, and we have some explanations, but we don't fully appreciate this yet, that it's actually much less problematic with this method than other comparable methods. So it's actually quite an impressive finding. So we still have to understand why this is actually superior, but it's a very useful thing to have. And there are other reasons why it's very good. It's not so much data manipulation, very simple to analyze, whereas other methods can have huge amounts of data massaging. There's systematic noise, the background noise of the sun can be modeled very well. And then we can directly apply to time varying systems like the sun. So we've done quite a bit on validation. So the method has been thoroughly tested, and we understand various things that have been independently observed using other techniques. We observe those same phenomena such as differential rotation, Rosby waves, and so on, and supergranular waves. So other types of phenomena that have been replicated using this method. So I just want to describe some of the methods, some of the results, sorry, and then I'll move on to other topics. So here is a comparison of convection, 3D convection, just like I described earlier, 3D global scale convection. This was simulated by Tata in one of the most state-of-the-art code, and so it's very fast code, and so on and so forth, and good physics and stuff like that. And this is a numerical simulation. We're looking at a specific radius, which is r divided by r sun is 0.94 in his calculation. And here is, we can also do the same thing at a deeper layer. I'm just showing this. This is for the sun. HMI means this is observed using seismology for the sun. And you see a stark difference between the features here and the features here. So these convective flows in the sun are all located near the equator, whereas they're, in fact, you can see if you look here, this is the same V theta and V phi. They're depleted at the equator, and they're sort of higher up in the high latitudes. And so you also see the scales of these features are much smaller here than here. So there's some very fundamental differences between numerical simulations, and I don't want to get into too much detail, but there are some significant unknowns on this topic, and we don't know what ingredients need to go into this numerical calculations to take this and bring it closer to this. But having more of these types of constraints and more of these images tells you it tells you what the true state of the sun is, and how, probably tells simulation people that they need to move numerical modelers, that they need to really change their codes to try to replicate this situation. Okay, this is another major problem that we think we can attempt with mode coupling because of its superior signal to noise properties. And are there Gmodes in the solar interior? And so, for a long time, it's known that acoustic waves propagate in the outer envelope, the convective envelope, but there are internal gravity modes in the interior. And these contain information about core rotation, deep interior properties, and so on. And if you can measure the oscillation frequencies of these Gmodes, then that would be very remarkable. So we have some ideas with which we might be able to infer these. This is a long way off, but it's still one of the most exciting future projects that we lined up using this technique. Okay, so now that's the broad topic of helioseismology that we work on. Yeah, I have one question from Pankaj Kushwaha.
Yeah, can you hear me?
Yeah.
Yeah, sorry, I don't work in this field directly, but I have just a curiosity. You said that in the numerical simulations, you have a significant unknowns or something that you're talking about.
Mm.
So like, okay, so you have one side is theoretical, and when numerical simulations are considered, okay, more or less within some limit, self-consistent, and you have observational. So how are you going to connect, let's say, the things that you derive from your analysis and the study to, let's say, some particular model, and still you convince that within those limit and the limit posed by numerical simulation, they are, let's say, okay, or one-to-one correspondence or something like that?
Yeah, it's a good question. So so basically what we want to do is we want to try to get as many constraints on the sun, on solar dynamics as possible using observational techniques. So for instance, we know differential rotation. So one of the first and most basic tests of a numerical calculation is, can it reproduce solar differential rotation in some robust way? And the answer is no, they're not able to reproduce solar differential rotation. So right then they fail a little bit, not because of want of trying, they work really hard, and then it's not an easy problem. There's some unknown ingredients, such as what is the correct state of turbulence in the sun? What's happening to convective features? Is it described well by mixing length theory, or is it described well by some other types of physical models? So there are some really fundamental unknowns here. And so right there, so you have one constraint is differential rotation. The other is the amplitudes of convective motions. We measure those as well using seismology. Can you reproduce the correct, or at least ballpark the correct amplitudes of convective motions? The third thing is, now this is a relatively new result. If this stands the test of time, then the next question is, can we try to replicate the flows, convective flows, with the geometric property that we observe here, that they're all located at the equator, so on and so forth. So that if you hit all of these milestones or these targets or these comparisons correctly, then you can say, well, this simulation is starting to become more trustworthy. Does that answer your question?
Yeah, just a naive clarification again. So like the things you said, that G mode or P mode are the things that you're talking about, right?
Yeah.
And using that as a probe of other things. So it is not heavily affected by, let's say, the things that you're talking about, like turbulence and these aspects. They don't have a strong coupling, right? So you can fairly.
Yeah, it's a very good question again. And in fact, G modes, the reason we don't see them at the surface and they're trapped, as you can see in this image, they're trapped in the interior, is in fact due to convection in these outer. This is the outer convection zone of the sun. So yeah. G modes and convection are opposite sides of the same coin. So it can either be G modes propagating, or it could be convection, and then the G modes are damped. So what's happening is these are trapped in this cavity, and as they proceed outwards, they become damped and they become really weak at the surface. So they are in fact interacting in some sense with the convection, and the convection is the other side in some sense of G modes. But P modes are also affected by convection. In fact, P modes are affected. P modes are acoustic modes. They're affected by all of these phenomena. That's how we observe them in the first place. We have if you go back to this thing, we have a simple model, and then we have a certain expectation for what the eigenfunctions of this simple model ought to be. But we know in the sun that the eigenfunctions are not these. There's something else. And so by measuring these couplings, which we can do in a relatively straightforward way, I haven't described how we do it, but we can. These couplings tell us what the type of convection is, what the type of rotation is, what types of non-axis symmetries exist in the sun, and so on and so forth. So it's because modes are affected by these phenomena that that's why we bother trying to measure all of these things.
Yeah, thank you.
Okay, so now I want to describe different to note what we do in terms of machine learning and how we try to extract new physics. So we have, especially in solar physics and heliophysics, we have an enormous amount of data, and there's a lot of different types of data. There's images, there's like single point measurements, and so on and so forth. And so you can basically, machine learning is very powerful because you can put all of these together, and you can simultaneously assimilate all of these data and make predictable outcomes, make predictions based on these. And so because the amount of data is enormous, humans are simply not able to process all of these data simultaneously. And so machines can. So if you train a machine well, it's very challenging to train a machine well. But if you train it well, then it can detect potentially these subtle features. And at least that's the hope with which we started this. And maybe we can try with some really challenging problems, like if you remember the movie that I showed you right at the beginning, one set of sunspots died away. They emerged, and then they sort of rotated around for a few days, and then they died. Another one came up and they became huge, right? So first, can you predict when new magnetic fields are going to emerge? Second, can you predict, are they going to be big? Are they going to be small? Are they going to vanish? How long are they going to last? So there is hope that perhaps there are other signatures at the surface that we are observing that we haven't known before, that are connected to these, that are correlated with these. So that was, at least, as I said, the hope with which we started this. And sometimes they do better than other techniques. They do better than humans, and we try to understand how they do this, how they achieve this superior performance. And this is known as machine interpretation. And we've done quite a bit of this actually to try to understand, because machine learning, as many of you know, is a black box, right? So it takes an input and produces an output, and what happens inside is very complicated to unpack. And so we've spent a lot of time trying to do this, because the idea is that if you do unpack it, maybe it tells you a little bit about the underlying physics. Okay, so let me show this movie. Again, many of you may have seen this already. Sorry, one second. Yeah, so this is a solar flare, for instance. If you keep observing this movie, and you can observe this for, because it's so spectacular, you can observe this for hours. I mean, there's a lot of other stuff. There's like sympathetic, I don't know if you can see, let me just, sadly, I don't think you can see my arrow, but if you're observing it, there are sympathetic reactions to this flare. There are other things that seem to be correlated with what's going on here. And so in this image, of course, is a very dramatic example of a solar flare. And so things an X-class flare, and there's a huge amount of high energy particles that are being blown out. But the question is, can we try to attribute this to some other physics? What's going on here? So on and so forth. And so flares were the thing that we started off with. And what we found was very interesting, and we collected all the M and X class flares. So flares are classified on the basis of the amount of radiation they emit, and M and X are on the higher end in terms of how much X-ray flux they emit. And so we used a machine. I won't really describe what we did, but ultimately here's what the machine seemed to recognize. We stacked all of these flares on top of each other statistically. This is time t equal to 0. This is when the flare happens. And the machine was trained to say, was asked, okay, if you give an image, or in this case, it is known as other parameters. There were other parameters, actually not images. But you ask the machine, is this going to flare or not, given this particular state of this magnetic region? And so the answer is either yes or no. Yes is a 1, and no is a 0. And so you can see that it's beyond 0.6 and it goes to 0.9. So it's very, very likely to flare. Yes, please. Pankaj Kushwaha.
Yeah, sorry. So these inputs or parameters that you are looking for, these are all observables and not related to any theoretical things, right?
There's no theoretical model. In fact, I was going to make a comment on that. In some ways, this is, but again, you have to be very careful when you train the machine, because you can introduce small biases in the training itself. But if you're very careful with the training, this is as powerful as or more powerful in some different ways as done in numerical simulation, because there's no bias. It's a model that's entirely based on data, and the model can be very it can be a high dimensional model, because you can use images and so on and so forth. So yeah. So what you see here is that the machine for days prior is seeming to say that this magnetic region is ready to flare. This for comparison's sake, this is what the machine produces if it's not going to flare. So we know when we train the machine, we know which AR is active region or magnetic region. We know which ones are going to flare and which ones are not, because we already obviously have all of the data. So we divide up the data into a training data set and then a test data set. The test is an unseen data set. And so when we apply it on the unseen data, you see that the machine is basically saying, for the flaring, for the ones that we know are going to flare in the test data, that is, machine is correctly predicting them, sometimes with very high accuracy, with increasing accuracy with time. And for non-flaring, it's very low. It's 0.1, as you can see here. So, so there's something about the magnetic configuration itself that, and so I don't want to get into it because this is a very long and detailed thing, but there's one property that we found was particularly interesting that seemed to increase with the time. Again, the x-axis is time here. Time t equal to 0 is when it flares. And this is one property known as ABS NJZH, which is an electric current. It's the absolute value of the electric current in that magnetic region. And this is a non-flaring region, a generic non-flaring magnetic region. You say that the absolute NJZH is 0 for that, not 0, but very small for that. But if it's a flaring region, you can see that it's rising cleanly and then reaches a peak at t equal to 0, and then it explodes, and then it gives out this, the electric current starts to dissipate, and then it drops again. And so that we found, this is known as current helicity, and rises sharply and then falls post-flare. So that was an unexpected thing. Okay, so I want to again switch gears. I'll be switching gears a few times here. So here is a result, again, using machine learning, where we wanted to look at 100 years of magnetograms of the sun. So we have really fabulous data from this Kodaikanal data set that, in fact, Dipankar Banerjee and others in the Indian Institute of Astronomy have been leading in terms of trying to digitize it and make it available to the larger community. So we were lucky enough to get our hands on this calcium K data set. So it takes images of the sun in calcium K, and we have basically 100 years of this. And so we trained what is known as a GAN. It's a generative adversarial network. And there's a generator and a discriminator. And what it does is we feed in this image, calcium K image of the sun. And we want to create as an output, we want the magnetogram of the sun. And there is an overlap between the Kodaikanal Observatory and the Michelson Doppler imager, which I described earlier, over a decade actually, or some years. And so we know this is satellite-based data. And so basically this is the input, and it knows that this is the true output. And so it reconstructs this, it translates the Kodaikanal Observatory and produces an image like this. Then you have a discriminator which compares these two. This generator compares these two and says that this one is similar to this, or it's a good match. Then the discriminator says, well, is the observed and the true, so the true magnetogram and the reconstructed magnetogram, are they good match to each other? And then if that is the case, then it provides a positive feedback to the generator, and then we train it this way. So we train it on basically on just a very few images, a handful of 300 or 400 images. We have, of course, several thousand images for the 100 years. And so just on that, and then that's it. And then, so for instance, 1989, is pre-MDI. So it's before what happened, before space-based observatories of the sun. And you can see that, yes, Dipankar, please ask.
Yeah, so I was just wondering, how did you, assign the polarity information?
Yeah, good question. Good question. I was going to get to it, but you asked it beforehand. You can't do it. In fact, so it does it, it guesses it, but there's the finite probability of error. So in some cases, because if it's trained well, it seems to generally guess it. So it's a guesswork. You don't exactly as you correctly anticipated. You can't get calcium, you can't get polarity, but it guesses. And so the absolute magnetograms are fine, but not the.
But when you say that the generator has used, I mean, I'm actually impressed that your fake reconstructed has produced this polarity information. So I mean, without the help of the MDI, you have done that? No.
So when we train it. So this stuff is without the help of MDI. This stuff is all without the help of MDI.
I'm just on the top panel. When you showed the third, sort of figure, yes, after the generator, the right side, the fake one, the reconstructed fake one. Yeah. If you do it in one step, it will be very amazing to reach at that. So it has to be quite a bit of few iterations, I guess, after that. Get that.
But not that much data in the end. Not that interestingly, just a few hundred images. So we just used maybe 2-3 years of data, and that was enough to basically train this very well. That surprised me actually how quickly it trained, which basically means that there's a strong correlation between this and this, and so it goes without too much difficulty. It's able to go from calcium K to, as you say, unsigned field. And it makes some guesses for this. It basically looks at the structure. This is my guess. We don't know what the machine's actually doing, but it's basically looking at the structure of the field and making some intelligent guess on about what the polarities of the field might likely be. And sometimes it works, sometimes it doesn't.
I'm just curious, since of course, the spatial associations and the correlations will be very good when you have a very good information also in terms of the rotation corrections and all that. You are aware. So I guess Ravindra has given you the L2 data, level 2 data, right?
That's exactly right.
The rotational correction. So there are certain errors in the version which I have put it in L2 in the KSO website. There are some more corrections. So maybe. We have a
talk actually. In fact, I've been meaning to write to you, and this is a good occasion in which to.
So get in touch with us because we have a better version actually now.
Yeah. In fact, I think Rajguru also told me you have you've worked a lot more on cleaning up the data. So I would like to work with you on this, and so maybe we can do that.
Yeah. Okay.
Great. Thank you, Dipankar. Okay, so we've then gone back and created a 100-year. Butterfly diagram, and so we can go to high latitudes. It's still work in progress. I wouldn't take this stuff too seriously. This is a super synoptic map of 100 years, and very nice data set clearly because it's working really well. You can see the clear butterfly diagram, the onset of the cycle, and the exit of the cycle, and the reversal, and so on and so forth. So again, very powerful use of machine learning. We hope to do some interesting tests on dynamo theories, the Babcock-Clayton mechanism, a good mechanism or not. We've only used calcium K, and we also plan on using H alpha measurements, which are available for this instrument, might provide us slightly better reconstructions. And the hope, as I said, is that we use this to understand some physics about what's going on with the magnetic fields in the sun. Okay, so now the last topic, I have a few minutes. So we want to do the ensemble seismology of stars. And so we know basically that all stars, all objects, presume oscillate. And so it's just a question of whether the signal to noise is sufficient enough to observe the oscillations. And so these are missions that have been, observing and will observe many stars. And so what's happening now is there are some machines. It's not to say that there's no machine learning at all, but at some fundamental level, people are spending an enormous amount of time and computational energy in fitting these oscillations. So what people do is observe these light curves, and there are minute scintillations of these light curves because of oscillations. You remove the systematics and the mean drift and some trends and stuff. Then you do a fast Fourier transform of the FFT of this, and then modulus squared. That gives you the spectrum, oscillation spectrum. You see a lot of noise, and then sometimes you see some peaks, which are the oscillation spectra. These peaks are very complicated sometimes, depending on the star. So red giants have very complex spectra. Delta Scuti stars have simply spectra just not understood. There are other stars have complex spectra and so on and so forth. The simple ones are solar-like stars, which are really clear and easy to understand spectra. But most other stars are not so easy to understand. But unfortunately, each spectrum rather, requires an MCMC, which takes a few hours, anywhere between 2 to 3 hours, and requires human intervention. Requires a trained human to look at it, not just any human. I couldn't do it. I'd have to become an expert, which would take some time. And then there's only so many MCMC experts or whatever oscillation spectra experts that are available. And so with Plato, we'll observe hundreds of thousands of targets, for instance. And so it's just not sustainable to do this type of computation any longer. And the idea is that if you have a good theory of oscillations, you go from these stellar parameters, the basic parameters such as there are certain parameters that are used to classify stellar spectra, like what is the spacing between peaks, what is the other parameters that I won't really describe in any detail, but we have a few parameters, like what is the rotation rate, what is the inclination angle of the star's rotation axis with respect to us, so on and so forth. Then you apply a classical pulsation theory. For different classes of stars, it's different. For Delta Scuti, we just don't even have a pulsation theory, but for the other stars, we do. And you can generate an oscillation spectrum. And the real question is, how do you go from the observed oscillation spectra to these stellar parameters? Can you go the other way around? And that's what I said is very expensive computation. It requires MCMC, a smart human to look at, etc. So what we can do is we can put a machine in between the observed oscillation spectra and stellar parameters, and this is feasible. We've demonstrated, and it's almost 9 orders in magnitude faster. I mean, it's ridiculous, of course, beyond the point, because it takes microseconds or a few milliseconds to go from here to here, from what would have taken hours to do before. So very remarkable. And so let me show you.
Sharavan, 5 minutes.
Yes, I'm almost done. Yeah, I really am almost done. So red giants, for instance, I just show. I'm only focusing on red giants here. They are proceeding with other targets as well. But red giant. So here's a blue is a theory of red giant oscillations, and you see these two keep repeating. This is just the simple L equal to 0 and 2. These are simple oscillations. For instance, even the sun has, and you see this very complex stuff in between here. This is known as mixed mode. So it's the acoustic modes in the outer envelopes of the star coupling with the gravity modes in the deep interior of the star. It's a very remarkable detection that came about a decade ago, because it allows you to get properties of the deep interior of the star, such as the rotation rate of the core and so on. But this mode identification in this case, and understanding what these modes are, what parts of the star they're going to, they're propagating in is non-trivial, and it's very challenging to categorize. So what we did is we trained a machine on millions of these spectra. We generated millions of artificial spectra. We trained the machine entirely on artificial spectra. and the machine was trained very well. And then we applied it on Kepler data. So this is all Kepler data. So we first have to test that the machine works, right, on data that have been obtained before, on estimates that have been obtained before. So these are for all stars that have been already analyzed, and this is one parameter called delta nu, which is the spacing between peaks. And you can see that with the exception of literally 4 candidates here, everything else there's hundreds of measurements here. They're all on this line. And this is the error, as you can see, is very good. It's very tightly contained to within 2%. And this is another more complex parameter. It tells you something about the core, because these are gravity mode. This is a spacing of gravity modes. And again, it's really good. It's a little bit larger. It's like within a few percent, but it's very, very accurate. And at some level, you don't even know if the MCMC is correct or this is correct. So it's pretty good. This isn't doing justice because there's only a few candidates that are outside of this straight line. Most of the candidates are densely, sitting on this line. And so when we train the machine, we don't actually impose any constraints. But it turns out there's an intrinsic, this has been known. We just rediscovered it. But there's an intrinsic correlation between this parameter delta nu, which is the spacing between peaks, and the gravity mode spacing delta pi. It has to do with the size of the outer envelope to the size of the core. And you can see this very clean relationship. This is from our inferences. And most people who do MCMC, for instance, they place a constraint. They say that delta nu is connected to delta pi through some linear relationship like this, and that's how they estimate parameters. But because we don't need to train anything like we train with no bias, and still we're able to recover this relationship. It's not new. It's just another validation that the method is working right. Okay, so I'm almost done. I just wanted to say, actually, I don't really need to say this stuff, but we're doing a lot of machine learning work. We're doing a lot of seismology work, different aspects of the sun, and so on and so forth. Yeah, exciting time. Thank you.
Thank you, Dr. Hanasoge, for a very nice presentation. So now we have time for questions or comments. So I request everyone to directly unmute themselves and ask question, or raise the hand and I will point you. Ritesh, go ahead.
Hello, Dr. Shravan. So my question is regarding that Kodaikanal data which you were showing. So how are you estimating the magnitude? Because I'm not sure the intensity calibration of those images are done.
You're not sure the intensity calibration is what?
Done for the Kodaikanal data.
I believe that, the data that we have from Ravindra are pretty good. They're good intensity, well enough calibrated at least that we're able to get reasonably good. When we compare, for instance, Kit Peak from 1989, we're able to get good reconstruction. So the way we get the first calibration between this is by training on MDI. So we train it on MDI data, and MDI data, of course, has good magnetic field calibration. So that initial calibration seems to apply to the rest of the data well enough, at least.
Okay.
Okay. So any other questions or comment? Pankaj, go ahead.
Yes, Sarwan. So on this Kodaikanal data thing, so like you can go from on image to get some, you can reconstruct, let's say, images based on observation.
Yeah.
I'm just perplexed, like, let's say, as you said, machine learning is very complex, so you have no idea what is going in between. So how ultimately, let's say, if you want to go into some theoretical aspect or like to connect with something, how you look forward to actually connect these two, given that the machine learning has quantified this part, but you don't know what channel and which one is the most important one?
Yeah, so it's a good question. So machine interpretation is a very active frontier of machine learning research, and so it's not fully clear. But we do a lot of engineering methods. So for so I haven't described. We've done other things like solar wind, trying to understand connecting solar wind to the surface of the sun. We've done other work on field emergence. It was there in this slide. I didn't really describe. But we've done like wind and flares and emerging active regions. So what you can do is you can put in an image, you can create a synthetic image, and you can put in different types of features, and you can put that as the input to the machine and see what comes out as the output, So in other words, you can create your own forward model that says, well, this is the calcium K I would expect, or for this calcium K, or for this magnetogram, this is the calcium K image. And you can use the calcium K image as an input to the machine and then see that the magnetogram is correctly reproduced or not. And so that in that manner, for instance, you can interrogate the machine. But that's just one method. There are other methods that you can proceed with.
Yeah, okay. And another just a quick question related to that movie that you showed, where you saw a solar flare and that just going out, and you say that there are a lot of structural perturbation probably you can see. So my question or worry is like, okay, see, what we are seeing is the intensity, which is results of dynamics happening and how the coupling between the radiation and the dynamics that is taking place at the surface or anywhere on the sun, right?
Yeah.
So how well are these coupling understood? Let's say that this kind of energetics will lead to this kind of radiation and things like that in case of suns. See, okay, I'm not sure if I am explaining it very well, but the thing is, okay, let's say this flare was due to something magnetic phenomena happening or whatever. And now that gives rise to emission. And through that emission, we see that, okay, there are wave oscillation or something is going on, right? The charge particles which are emitting are coupled to that magnetic field or whatever is there and within that environment. So my question was like, something happening on the dynamics, whether magnetic field, and then the transfer of that energy to charged particles and this coupling, which eventually lead to radiation. How well do we understand it in the case of sun?
I mean, I think there are some theories definitely for it. It's not to say that we don't. There are people actively, for instance, doing numerical simulations to pursue the very questions that you're talking about. It's an active area of research. That's maybe the easiest way to say it. Some things are known, some things are not. And it's still, whatever new light can be shed on these topics using whatever constraints. So this, for instance, this approach that I'm describing may not necessarily provide insight on the specific way that you pose the problem, which is the connection between radiation dynamics and radiation and transfer and dynamics and so on. But it provides maybe other constraints on the model itself.
No,
so,
okay. So I just wanted, because okay, sun is the nearest one. The other thing is because everything measure is images, right? Photons mostly are the charged particles. That are the only two messengers. And then we go and infer the things about something related to dynamics. And that involves this additional step of how the couplings are, these things are. So that's why I asked. Okay, thank you.
Yeah.
Okay. Kishore, please unmute yourself and ask the question.
No, so I had a question about this normal mode coupling technique. It disagrees with some other helioseismological techniques, right? So do we understand why that disagreement is there, or where the error lies?
I mean, so okay. So I mean, is there any specific result that you want to?
No. So the specific result was basically this thing where you find that the usual simulations, they underpredict the convective velocities deep in the convection zone.
Oh, right.
Yeah.
So I mean, why numerical simulations don't work, I don't know. That's not really
no. So there are these other helioseismological observations which use some different techniques, and they claim to find something which agrees with simulations, right?
Yeah. This opens up a more complicated thing. You're talking about the amplitudes of convective velocities.
Yeah, the amplitudes of the velocity.
Yeah. So I think there is general agreement now, even though it's not necessarily published, but there is general agreement, including the other group that had this different inferences. There is general agreement that amplitudes are low. We certainly know at the surface, for instance, if you plot the surface convective power, that also displays anomalously weak convective velocities. So there is general agreement now. Those guys who did different results, by the way, we didn't use normal mode coupling for that. That was nearly a decade ago using a different method. So it wasn't really normal mode coupling for the convective amplitudes. But okay, anyway, suffice it to say that there is a general sense of agreement now.
Okay, yeah, thanks.
Okay, Dipankar, please go ahead.
Yeah, just to add some more discussion in the forum and to bat for Shravan. So the flare thing, where this is more relevant for what Pankaj was asking. you see the flare prediction and all that, it's only possible for us to do sort of the association business or the timing and so on. It's much harder to really talk about the energetics. What you are looking for is really how much energy and all that, how big these flares and all that. So what I think we are able to do now only is the complexity of the active region, looking at the evolution of that complexity of the active region. You have a prediction probability, and that is important because of the timing of the flare is important to predict when it is happening. And to some extent, the complexity of the active region, its energy content and all that, also giving you the rate at which the complexities are changing and all that, giving you a hint on the scale of the flare. So that's maximum.
That's
one
right.
thing.
Yeah.
And actually one more discussion, if you show Shravan the synoptic, super synoptic, this is the an important area. Why it is so important is the magnetic field measurements, regular magnetic field measurements are only available for last say 3.5 decades.
Yeah.
Or a little longer than that, but not certainly before 1970s. So there are no magnetic measurements at all.
Exactly right.
So to have an idea at least how the magnetic field evolutions were, at least in a global scale, that's the attempt one can make. Again, quantification is also a challenge. As I was asking about the polarity information is demanding, because
do you anticipate, Deepankar, that H alpha will be able to shed any light on it or no?
Yeah,
right?
so we are doing that. So we do have a super synoptic magnetogram for the past century, including the H alpha, calcium together, because H alpha will give you the location of the neutral lines, and then use the calcium as the location of the association of the magnetic field location. Combining these two information, you can get a polarity things also, and the polar rush and all that. So this is done with the Russians. There are a few publications on this regard, the super synoptic stuff. The other thing is very challenging, which again will probably Pankaj would have been thinking in that line, is the measurement of the sort of quantification of the field. Now, what we can only say that here are the locations where magnetic fields are, but precisely how strong the fields are needs a very good calibration between the calcium intensities and the magnetic field. Since these are all digitized data, and the digitization process, has a lot of challenges in terms of, calibrations across all these 100 years and so on and so forth. That calibration is very, very difficult. So these super synoptic magnetograms are actually showing, of course, Shravan has given a bar chart. That's why I asked you to show this. But this is very preliminary. I don't think we are in a very good shape to say about the strength of the field that much.
That's good to know, Deepankar. You know what we'll do? I'll ask my student postdoc. We'll present to you, and then maybe you can criticize our results. Sure. Very good to know.
Yeah, because what happens, Shravan, the data what you're using from Kodaikanal also, for example, we have issues in terms of its intensity calibration.
Right.
At different times, the plates are of different quality, and the developments and all that. So we do not have an absolute calibration of intensity. So unless you have an absolute calibration of intensity, you cannot convert intensity to magnetic field.
That's right.
So what you will do, we will have a lot of errors. I mean, uncertainties will be too much. So we have not attempted to do yet the field, quantification, but only the polarity and some, as you rightly pointed out, combining H alpha and calcium, we can get some, hint of that. Because this polar rush business is very, very important, because that is involved with the polarity, reversals. And
that's really good to know. Okay, so we'll discuss this at greater length. I really want your thoughts.
Sure, we'll be happy to do that. Yeah. Thanks, Shravan.
Okay, Indranil, please go ahead.
Shravan, so again, my question is related with the magnetic fields. So now, if the magnetic field of the star is stronger, So does that enhance the oscillations, or all these acoustic modes? Does it enhance that, or it suppresses it?
Well, we know for the sun, for instance, the frequencies increase in times of magnetic maxima, and the frequency relative to the magnetic minima. So in other words, what's happening is the waves are sped up. Generally what happens when you have a magnetic field is that they add a very simple model of what a magnetic field is doing. It's much more complicated because they have geometric effects and stuff. But if it's just the effective sound speed is increased by the magnetic field. So the waves are going faster, and their effective frequency therefore slightly increases. So when you observe, just measure P mode frequencies as a function of solar cycle, you see a very clear increase in frequency with cycle. So does that answer your question?
Yeah, but the only point is, what I was trying to understand is that the average magnetic field of the sun at some at some depth or at some height, whichever way you want to see at it, that does not change much, right? It is on an average, it's 1 Gauss or something. But if we go to a star which has intrinsically stronger magnetic field, I mean, in those cases, what is your guess? I mean, how it's going to pan out?
I mean, you have magnetic splitting, for instance, and so when you go to distant stars, you can only observe spectra, right? There are oscillations of a very few modes, right. Very, very large scale modes. And so you'd have splitting, they would split, just like if you have rotation, you have splitting of modes, Zeeman splitting. And so you'd have, clear Zeeman broadening or Zeeman splitting. And sometimes, for instance, in red giants, modes disappear. An entire branch of modes appears to disappear. So you see this, the stuff in between. So for some red giants, these are anomalously weak. They don't seem to even exist. These are known as the L=1 mixed modes. These modes here, this forest of peaks here, is a coupling between the P modes of the envelope and the G modes of the interior, and they vanish for some red giants. And so there's a group of people who have speculated that it's because of the magnetic field in the core that's just dissipating away all these waves. Not dissipating, but they're channeling them. They become like a waveguide and they move them away, and so you don't actually even end up observing them. And so these vanish. So there could be all manner of effects of this sort.
Mm-hmm. Okay.
Okay. So if there are no further questions, so we have reached to the end of the seminar. So let us thank the speaker once again. So thank you, Sharavan, once again for accepting our invitation and delivering the seminar. Many thank you, and hopefully things will normalize and you will be able to visit us sometime soon.
Yeah, I look forward to it. There appears to be one question from Indranil Chattopadhyay.
No, I asked.
He already asked.
Yeah.
Right. Okay. So thank you, Shravan. Thank you everyone for joining, and then we will see you next week. Okay. Right. Bye-bye. Have a nice day.
Dipankar, I'll be in touch. Thank you so much for your comments. I'll be in touch.
Yeah, sure. Okay. We'll be happy. Yeah.